Good afternoon, morning, or evening, Math Foundations people. Today we're going to be looking at equations of sine and cosine and how they compare to the original equation. So when we put some numbers in there, like in front of the sign or beside the sign or in brackets, what happens to the curve? Okay, if you've taken pre-cal, you would call these transformations. If you haven't, that's okay because we're going to go over them today. Okay, we'll get our blackboard open here, and what we're going to look at today, probably break this into 2 days. We're looking pretty good here to get done here in early June, pardon me. Right now, I'm working on the 24th as my approximate date here. The 25th is a Friday, that's Vanguard grad, so I probably won't have anything up for that day. 26th, 27th will be the work weekend, 28th, 29th. So in there, in the very end of May there, and the very beginning of June, we should be working on our handed and getting that done. So within the first week of June, or by the second for sure, we should be finished the course. And then working on I'll put some videos up for some practice here, for some final exam practice and things like that. Put the rules down for the final exam as well. What I think I'm going to do for the final exam is I will provide you with the previous formula sheets from the last exam that I gave you, but I also will give you the opportunity to make up a formula sheet, cheat sheet if you like, one sheet like this, and you can write all your equations on there with little notes on what part they come from or whatever to use during the exam if you want. Okay, so that'll be in the final exam. We'll talk about that more at the very beginning of June. Okay, and then your exam should be scheduled in your school. It can be scheduled on the exam day, or it can be scheduled, as soon as we're done the course, which will be early June. If I'm looking at the calendar right now, I'm looking at probably be done by June 8th for most of us that are on task. That are right with me right now on the approximate dates. If not, there's an extra week or two in there. June 18th is the last day to hand anything in, if I remember. Let me look at June here. I think June 18th will be the last day to hand anything in, which is the middle of the week somewhere, so that I can get everything done. Okay, so let's get started. What we're going to do today, we're going to use Desmos mostly. And we're going to, if you've got a Chromebook around, you can use that, or you could just follow along with me. We're going to look at the effect on some curves. So let's just kind of outline what we're going to do today. Let's see here. Okay, so, and also, I think this will be my last year of putting Math Foundations up online. I think we had some changes in cyber school, and I'm moving into another class, and this one's going to the person that does Math Foundations in grade 10 and 11, which is fine by me. But we will go along here with, what day are we on here? Day 11. Okay. So this is unit 4. Okay, and we are going to be looking at equations of sine and cosine today. And in that, we're going to be looking at the effects. We're going to do the effect of 4 different positions, 4 different, we'll call them transformations. That's what they are. Okay, and we'll see those 4 different, and I probably won't get to all 4 today. Well, we might, we'll see. And then we're going to summarize, and then we'll look at some examples. I imagine the example questions will come tomorrow, and we have to do degrees and some radian ones. We haven't done a lot of radian ones, so another day or so of that. As I was mentioning today, being the 24th, my approximate day, it's actually not the 24th, it's some other day in May, but the day that I'm doing for my approximation. So tomorrow is a Vanguard grad day. I don't think I'm going to put up a video for that day. So Friday you can take off, and so our next video will be like May 28th, I think. Okay, so let's go ahead and let's bring Desmos over here and set it up first of all. So the first one, or let's set up what we're going to do first. So first of all, we're going to compare y equals sine x and y equals cosine x to y equals sine, or a sine x and y equals a cosine x. Okay, so what happens where area is a number? Where a is an integer. Okay, so we're going to use this. Whoops. There we go. And we're going to use this to summarize our notes on it, but I'm going to bring up Desmos here. Oops, that's not Desmos. Which one is it here? Right here. Okay, so let's set up our graph. We have to have, because there can be some changes in it, we're going to set it up bigger than a bigger window, I guess is the best word for it, than we normally do, than one period. So remember that it's going around the circle, it's 360 degrees. So let's go into the wrench and put it in degrees first. Okay, and let's change it from, in the x-axis, let's go from 0, the start of the circle, and let's do 2 circles. Actually, let's do 1 circle. Yeah, let's do 1 circle. One. No, we better do 2. We better do 2 circles. Let's do 720 degrees. That's 2 circles, okay? So that means it's going to repeat itself, and then we'll go from there. So go from 0 to the 720 degrees. That's 2 circles, 2 unit circles. And let's go from y. Let's go from -4, +4. So that our window, remember with the unit circle, it only goes from 1 to -1, but we'll make it 4 times bigger. So there's our window. So then we'll just put in the regular sine graph. Y equals sine x. Okay, so there it is in red. Nicely done. It's going up. Here's our maximums at 1. Okay, notice that there's 1 circle at 360 degrees and it does another circle. So it's repeating. There's 2 periods in here. Okay, we see that 2 periods in here. It's going up to 1 and down to -1. It's crossing at the same place it always does. Okay, here it's 0 and then 180 and then 360, and then it repeats itself in the same type of order. Okay, that's the sine graph. Now let's put in a value of a number in there. So let's go y equals 2 sine x. Okay, look at the difference that you see here. What did the 2 do to the graph? Okay, so you thought about it there. As you can see, it didn't change the x-intercepts. It's still 0 where it's 0. It didn't change the maximum and the minimum. It still occurred at 90 and 270. And then when we repeat it again here and here, didn't change how many bumps we have. We have 2 bumps there and 2 troughs there. Okay, but it did change the height of the graph. Okay, so what if we put y equals, we can predict here, what if we put y equals a half, 0.5 sine x? Okay, and there we have a smaller one. It only goes up, the maximum only goes up to the half mark here, and the minimum only goes down to the negative half mark. Okay, so it has changed. A affects the height of the graph or the amplitude of the graph if you use the words that we used last day. Okay, so that is pretty straightforward. Now, what do you suppose happens if I throw a negative in there? Instead of negative 2, I'll put -2 in. So let's erase these other 2 here. Let's keep the sine graph there. And let's type in y equals negative y equals -1 sine x, or just negative sine x. Oh, I got to put them together, I guess. Oh no, they want me to put it in brackets. Okay, so we have to type bracket -1 bracket sine x, because they probably don't. Probably just put. Oh, that's because I have an m there. That's why. Stupid me. Y equals -1. So now we should be able to do sine x. There we go. It's kind of in the orange color. They're very similar. And you can see that it's opposite. Wherever we had a negative value, a maximum, we now then have a minimum. Okay, so there's a minimum at 90 instead of a maximum. So it's flipped it upside down, which makes sense. Okay, if we throw in a -2, it should be twice as high. Right, throw in a -4, 4 times as high. Okay, so that a value affects the height of the graph or the amplitude of the graph. If it is negative, it switches the maxes and min values, or flips the graph around. Okay, so let's summarize what happens on our notes. So we'll bring this off to the side. Oh, maybe we should try cosine. We only did sine. So if I throw in cosine here, and I change this graph into, let's say, 3 cosine x, you can see that it's the same shape. It's just that cosine always starts at a maximum rather than starting at 0 like sine does. Okay, so the same thing happens with cosine. Cosine and sine the a has the same effect on it. Okay, so let's move this over and summarize it up. So let me just shrink my Desmos down here. Okay, so let's summarize what we found out here. Let me just click over back in here. Okay. Okay, so the a value determines the amplitude of the sine or cosine graph. Okay, which is height of the sine or cosine graph. And that's what we found out there when we did that. Example. Y equals 4 sine x has an amplitude of 4. Okay. The other thing that we found out, if the a value is negative, if the a value is negative, then the max values are switched with the min values of the original graph. The max values of the original graph become min values of the transformed graph, we'll say. Okay. And then we can also say it as well. The original min values become transformed max values. Okay, so just a little sketch of our diagram here. If we can just do this quickly for our example. Okay, if we just do a little, remember our T-bar sketch, 90 degrees, 180 degrees, 270 degrees, and 360. There's one circle. Okay, we'll put 4 up here and 4 down here because we have our example goes in 4s. Okay, so our example 1, put a max there and a min, a 0 there, and a min there, and so if we go, just do our little example here. Oh, those, I missed that one, sorry. Okay, there's a sketch of our example, that what it would look like, except it should be crossing with my tick right there, but I didn't get it perfectly spaced in my little sketch. Okay, so that's the effect of A. Okay, let's pop my preview up to see how long that took here. And then we'll do our next one, which will be the effect of B, which we'll put in front of the X. Okay, that was about 17, 18 minutes. So we'll probably get 2 of them done today, and we'll do the other 2 tomorrow. We'll see how it goes. We even get 3 out of the 4 done. Okay, so that's the first comparison. So in our notes here, let's go ahead and do this on the next page. Okay, so we're going to compare the next one. All right, so let's bring her up. All right, so we're going to compare comparing y equals sine x or y equals cosine x to, and we'll do it in blue again, just like we did last time. There we go. Y equals sine bx. So there's a number in front of the x, okay, and we can put this in brackets just so that we know that we're multiplying those 2 together, okay? It doesn't necessarily have to be in brackets, but sometimes it does when we do the next type of add-on. So we're just going to put it in brackets. Or y equals cosine bx. Okay, and we'll see what happens when we do that on Desmos, okay? And then we'll summarize our notes here. So let's bring Desmos back here. I always get the wrong one there. Okay, so let's erase these 2 graphs here. We'll keep the same window that we have from 0 to 0 to 720 degrees. Okay, and we will start off with the let's start off with the cosine graph. Okay, well, no, let's start off with the sine graph. I think it's easier to see on the sine graph. So let's start off with the sine graph. y equals sine x, okay? We've got bump number one, bump number two, trough number one, trough number two. Two revolutions of the circle as we're going around. Okay, now we're going to get into y equals 2 sine x. Sorry, y equals sine 2x. We did 2 sine x already. Y equals sine 2x. Purple there. Okay, notice that if we just look at where the x-intercepts and y-intercepts are, it has some common ones right there and right there and right there and right there, not right there. The purple one has twice as many x-intercepts. It also has twice as many bumps. So there's one bump here, but there's 1, 2, 3, 4 bumps. There's 1, 2 troughs there, but there's 1, 2, 3, 4. Okay, so it's doubled the amount of maximums and minimums that we've had. But in reality, if we look at the period, there's one period to 360 degrees of the red graph. There's 2 periods all the way to 720. This one here has 1, 2, 3, 4. So it is shorten the period because there are 2 of them in the same amount of degrees. So this means the purple one has rotated around 4 times, where the red one has rotated around only twice. So that means the purple one, 2, has shortened our period by a half. So if we took the 2 and took 360 degrees and divided it by 2, we would get 180. Let's see if 180 is one period. Okay, right there's the first period. Is that 180? On 0? Let's see if I can get it on 0. Yes. So the first period of the purple graph ends at half the distance that it should have if it was not transformed. Okay. What about if I put a 3 in there? Okay, what has happened here? In one period, let's go, there's 2 periods here for the red graph. So this one has 1, 2, well, let's do it right. 1, 2, 3, 4, 5, 6 periods rather than 2. So it has tripled the amount of bumps here, or it's made it 1/3 as big. So if we took 360 degrees of the original period, we should have, and divided by 3, which would be 120. This should end at 120. One period should be at 120 degrees for the purple. So is this 120 right here? Indeed it is. So this number in front of the x determines the length of the period of the function. Okay, if you have a number that's whole, you divide the number into 360, which is the original period of the original graph, and that's how much how many multiples, or you could say the number is how many multiples of the period you'll see, so that if you divide it by 360, it'll give you how long one period is of the transformed graph. Okay, what if we put a half in there instead of, okay, instead of putting in 3, I'm going to put 0.5, or 1/2. Okay, notice that this time, 0.5 for the purple, we only got 1 period here. 1 full period. Yet the red graph has 2 full periods, which is the original graph. So this one took 720 degrees to complete one period, whereas the red graph completed 2 periods, which is the original sine graph. So if we took 360 and divided it by 0.5, would that give us 720? And indeed it does. Okay, so this number in front of the x determines whether or not, the length of the period. If it is 1 or above, it's going to shorten the period. If it's less, from 0 to 1, it's going to lengthen the period. Because when you divide 360 by a decimal number, it makes it bigger. Okay? What if you had a negative in front, you're thinking? Okay, what if I had y equals negative 2 sine x? Okay, you'll notice that the negative value, again, changes the max and mins. Okay, if I just put negative x there so that we can see. Okay. There's negative 1x. Okay, so it's changed the max and mins. Okay, and you're like, well, didn't change the period. No, because negative 1 into 360 is going to still be 360, but negative, flip it over. Put negative 2 in there. Oops, got 2 negatives, sorry. Put negative 2, it flips it over and shortens period. Put negative 0.5, flips it over and lengthens the period. Okay, so let's summarize what we found out for A in front of that graph. Okay, so let's get Desmos out of the way here. So the effect of B. Okay, so graphs in the form of y-axis, comparing them, let's say the first point here. Okay, the value of B determines the length of the period of the function. We'll say period length of the function. Okay. Okay. If you use 360 divided by b, so this is a divide by sign, this equation will determine the length of one period of the transformed function. Okay, so under that, thus, if B is 1 or above, the period shortens. Okay. If B is a fraction of 1, okay, so that means from 0 to 1, not including 0 or 1. We'll say greater than, we'll do it with greater than equal signs if I can find them on here. Okay, so this would mean that B is greater than 0, but less than 1. Okay. oops, period lengthens. Okay, and the last thing, of course, if we put a negative in there, if b is negative, the function max and mins flip. Flip in the transformed graph. Okay, so that's two of the values we want to look at, and I'm going to put quote marks around flip. That's two of them that we want to look at. We'll look at the other two here, but I want to go and I want to do some radian graphs just to show you how radian graphs look a little bit different, okay? So we're going to go back to Desmos. We're going to do a couple of radian graphs, and that'll take us to, we're at 31 minutes right now, so that'll take us to about 40 or so. And then we'll do the next two tomorrow, and then we can look at some of the practice after that as well tomorrow. Okay, so let's flip this back in here. Whoop. Oh, wrong one. I'm moving the wrong one. Sorry, guys. I guess we should do an example like I did in the other one before I do the radian stuff. So let's do an example here. I forgot about that. So an example. If we do the example of y equals sine 2x, we can draw this out pretty simply. We do our t here. Okay, now we're going to have two periods in the 360 degrees. So I'm going to go and I'm just going to draw 8 ticks instead of 4. 1, 2, 3, 4, 5, 6, 7, 8. So that's going to be my 360. So we're going to have 2 periods here instead of 1. It's going to be shorter. So in our example, this would be 0. Oops, let's make that smaller. Okay, then this would be 90. So this would be halfway in between would be 45. This would be 180 if you're doing regular one. So that halfway in between that would be 135. Okay, this would be 270. So halfway in between them, that would be 225. I'm going every 45. This would be 315. And this would be 360. So if we were doing just up to 1 and down to -1. So this graph would look like this. You would have 2 periods. So there's 1 period of the graph right there, but it would repeat itself again. So the key to drawing a sine graph is you go 0, usually it's 0, 90, 180, 270, or 180, 270, and then that way. So this, I just did 2 of them. It follows the same pattern. So this is the example that we would have here. So we can see that we have 2 periods in 360 degrees. So this would be, we can see that there's 1 period. Oh, went too far. Let's fix that there. It only goes to 180, right? It's got to come back to the 0. Okay, 1 period, and then 2 periods. Okay, the original one would just go, sorry, would go Okay, so that takes us, well, now for sure we can only do 2. Let's do a couple of, let's just take a look at an example of radian ones, just because we haven't used radians yet. So let's try one with radians. Okay, so we'll keep that here. Oops. And we'll move Desmos back up here. So let's just plot a radian one. Where are you, Desmos? Hopefully I didn't close you off here. I think I put it behind. Hold on, guys. I'm just going to find my Desmos again. Sorry about that. Okay, so if we're going to do a little bit on radians, let's close these off. So the big difference, we'll keep that there. The big difference is if we're going to do radians, we have to click radians. Look at all that. Whoa. But the reason it's doing that is because we have to change the x value not to 360 or 720 radians. 2 pi radians is 1 period. 2 pi is only 6.321 or 6.28321. What am I doing? Okay, so let's go from 0 to 2 pi. 2 pi. Okay, 2 pi. I'm going to just bring this keyboard up. It should have pi on it here somewhere. I always forget how to get the pi on here. Oh, there it is right there. 2 pi. 2 pi pi. I did two pi's. So there's 2 pi. So you notice that if you put it in radians, that's 2 pi radians, 6.28 something, right? 3.14 times 2. So radians, if you're doing it in radians, you'll notice that the maximum is at pi over 2, which is 90 degrees here, and 1. The second x-intercept, if you notice it here, we'll get on it here. Can't get it right on. Anyways, it's going to end up being 3 pi over 2, but they don't put the pi in there in that one. They just do it for these two here. So, oh, sorry, 3 pi over 2 is the minimum. This one here is 180, which would just be pi. 3.14 right in there. But they don't want to really put the pi in there for that one for some reason. I don't know why. And this one would be 2 pi. Okay, so that is radian graph. So you can do it in radians as well. And the difference when you see a radian graph to a degree graph is that with radians, there's no degree symbol in there. Okay, so then you know it's a radian one. If there's a little degree symbol in there, then you know it's degrees. Okay, and we'll get into C and D tomorrow. I think we've gone about 39 minutes now, so we'll close this up for today. Okay, so looking back at our notes, just to summarize. Okay, bring this back up. Okay, just to summarize, A, the number in front is the amplitude, determines the amplitude. Okay, the bigger the A value is, the higher the graph will go. If A is negative, it flips the max and min values. There's an example. B, if you take the B value, which is right beside the X, the B value determines the period. If you take the original period of 360 degrees and divide it by B, this will determine the length of the period. So therefore, if you have a 2, you'd have period being 1/2 as long. So instead of 360, it's 180. Or another way to look at it is you had a 2, you'd have 2 periods in the original 1 period. If you had a 3, you'd have 3 periods in the original 1 period of 360 degrees. Okay, and if it is negative, again, it flips around the graph. Okay, so that's our summary for today. Tomorrow we'll do the other two, and then we'll do some practice as well. Okay, we'll see you then.